Imagine a place where gravity is so powerful that nothing, not even light, can escape. These are black holes, real cosmic enigmas that challenge our understanding of space, time, and existence. They ignite our curiosity, pushing us to explore the unknown and ask, what's in there? Today, we'll take a journey, not just to observe, but to plunge into a black hole, where Einstein's relativity and quantum mechanics collide. By imagining this impossible voyage, we test the limits of our knowledge and confront the universe's deepest secrets. Falling into a black hole is gravity's ultimate triumph, a one-way trip into the heart of mystery. So, strap in, the cosmos is waiting. The allure of the black hole is the allure of the ultimate frontier, a boundary of comprehension shrouded in profound enigma. What exactly is a black hole? Imagine crushing a massive star into an impossibly small space, so dense its gravity warps reality itself. When a giant star collapses, it leaves behind a singularity, a point of infinite density where physics breaks down. Surrounding this is the event horizon, the point of no return. Cross it, and not even light can escape. The event horizon isn't a surface, but an invisible boundary in space. There are stellar mass black holes just a few miles across, but with the mass of many suns, and supermassive black holes millions or billions of times heavier, anchoring galaxies like our own. At the center of the Milky Way sits Sagittarius A*, a supermassive black hole. A black hole is less an object and more a region where gravity dominates, warping space-time into a cosmic waterfall. It doesn't suck things in like a vacuum. Instead, objects are swept along by the current of space-time itself. This is the stage for our journey, a place defined not by what's there, but by what can never leave. Black holes are the ultimate test of our understanding of the universe. They are regions where the familiar rules of physics are pushed to their breaking point. To truly grasp their nature, we must venture closer. Let's begin our descent. Our journey starts far from the black hole, where it's invisible, detected only by its effects on nearby stars or the glow of an accretion disk. As we approach, gravity feels normal, like orbiting a star, but unlike a star, there's no surface, just a deepening gravitational well. The closer we get, the stronger the pull, and the more power we need to resist being drawn in. Imagine we cut the engines. Now, we're in free fall, toward the event horizon. Inside the ship, everything feels normal, weightless, as in orbit. Gravity and acceleration are indistinguishable. But to a distant observer, our time slows down, an effect called gravitational time dilation. Our ship appears to move slower, its light redder and dimmer, as we approach the event horizon. To them, we seem frozen on the edge forever, but for us, time ticks on and the horizon looms closer. The black hole's pull is relentless, and our fate is sealed. The journey is a slow dance with destiny, where every mile brings us closer to the unknown. The universe outside fades as we approach the point of no return. Our perspective shifts, and the laws of physics begin to warp around us. The event horizon is now within reach. We are about to cross into a realm where escape is impossible. The final moments before crossing are filled with anticipation and awe. The edge of forever awaits. Crossing the event horizon is surprisingly uneventful. No jolt, no bump, just a silent transition. For a supermassive black hole, the gravitational forces at the horizon are gentle. We drift across the invisible line, our fate sealed. Looking back, we'd see the universe's future play out in fast forward, stars born and dying, galaxies colliding, the cosmos aging in moments. Time outside races ahead, while for us, seconds pass as normal. Inside, space and time swap roles. The singularity is now a moment in our future, not a place in space. Every path leads to the center. Escape is impossible. We are cut off from the universe, trapped in a bubble of warped space-time. No signal can escape. Our reality is fundamentally altered. The journey from horizon to center is swift, microseconds for a small black hole, hours for a supermassive one. The pull of gravity is absolute, drawing us ever inward. Our past is behind us, our future is the singularity. The event horizon is a one-way door, and we have stepped through. The universe outside is lost to us forever. We are now part of the black hole's story. The final plunge has begun. There is no turning back. Just before crossing the event horizon, the view is surreal. The black hole's gravity bends light, creating extreme gravitational lensing, a cosmic funhouse mirror. We see stars and galaxies warped around the black hole, sometimes appearing multiple times. A bright Einstein ring frames the darkness, formed by light bent perfectly around the edge. We might even glimpse the back of our own head, as light circles the black hole and returns to us. The event horizon grows, filling our view. The universe behind compresses into a shrinking blue-shifted window. Colors shift to brilliant blue, then ultraviolet and X-rays as we fall into the light waves. Space folds in on itself and straight lines vanish. The sights are both terrifying and beautiful, a final psychedelic light show courtesy of Einstein's equations. This is the universe through a lens of pure gravity. As we fall, especially toward a smaller black hole, we feel tidal forces. Gravity's strength varies dramatically from head to toe. This stretching and squeezing is called spaghettification. For a stellar mass black hole, these forces would tear us apart before we even reach the event horizon. That's why we imagine falling into a supermassive black hole, where the event horizon is farther from the singularity and the tidal forces are gentler at first. But deep inside, spaghettification is inevitable. Matter is stretched into thin streams, atoms pulled apart. Stars that wander too close are shredded in spectacular tidal disruption events, their material forming luminous noodles of gas. This is gravity's ultimate power, not just theory but cosmic reality. The fate of any matter, star or astronaut, is the same: stretched, compressed, and consumed. Spaghettification is the grim end awaiting all who cross the threshold. It's a violent, spectacular demonstration of the black hole's might. At the singularity, our understanding collapses. General relativity predicts infinite density and zero volume, a place where physics breaks down. Our equations fail, signaling the need for a new theory: quantum gravity, uniting relativity and quantum mechanics. Some ideas suggest the singularity isn't a point, but a Planck star, matter compressed to maximum, not infinite density. Others propose the fuzzball model, where the black hole's interior is a tangled mass of fundamental strings with no singularity at all. These theories aim to resolve paradoxes and preserve information, but the true nature of the singularity remains unknown. The heart of a black hole is the ultimate testing ground for new physics. It's where our best theories meet their limits. The singularity is the greatest mystery in the cosmos. The breakdown of physics at the singularity sparks wild ideas. Could a black hole be a gateway? Wormholes or Einstein-Rosen bridges are theoretical shortcuts through spacetime, possibly connecting distant points or even other universes. But these structures are thought to be unstable, collapsing if anything tries to pass through, unless exotic negative energy matter exists. Some theories suggest black holes could spawn new universes, each a cosmic nesting doll within another. The fate of information, whether it's lost, preserved on the event horizon, or reborn in a new universe, remains one of science's deepest puzzles. Black holes force us to question the nature of reality itself. Here, science, philosophy, and imagination converge. The interior of a black hole is the ultimate laboratory for the unknown. Why study black holes? Because they are the universe's most extreme environments, testing our theories to the limit. Observing how light bends, how stars orbit, and how black holes collide lets us probe Einstein's relativity with unmatched precision. Supermassive black holes shape galaxies, regulating star formation and galactic growth. Studying them pushes technology, like the Event Horizon Telescope, which gave us the first image of a black hole's shadow, and LIGO, which detects gravitational waves from black hole mergers. Black holes are the edge of our knowledge, holding keys to the next revolution in physics. They challenge our deepest intuitions about space, time, and information. The journey into a black hole may be one way, but the quest to understand them expands our cosmic perspective. There is still so much more to discover.